Hi everyone, this is Ali. Um, Today I'm going to talk about my machine learning term project, which was about credit card fraud detection. The dataset was obtained from Dataflare website, uh, which you can see here, and it contains transactions made by credit card holders in September 2013 in European countries. It's for the course of 2 days. It has about 285,000 transactions. The dataset has 30 features, um, which are principal components of some unknown features, which have not been shown due to confidentiality issues, and they're all numeric, so we don't need to make any transformations, etc. And the goal of this project is to predict the fraud transactions in the data set. And I think the most important thing about this data set is that it's highly imbalanced. So the ratio of positive to negative classes are 1 to 580, which means accuracy wouldn't be a good measure to assess the performance of our classifiers. So yeah, so this is a classification problem. Accuracy is not a good measure just because if we start with a no skill classifier and say, hey, predict a class 0, no matter what the input data is, then we will end up with the accuracy of 99.8%, which obviously is not a good way to measure the accuracy of the model. I will use AUC as a measure of performance of the classifiers, and here are the summary of the classifiers that I will train and use to predict the fraud transactions. So basically all all classifiers are some the ones that we use for classification type problems, logistic regression, SVM, KNN, artificial neural networks, random forests, decision trees, and gradient boost classifiers. And so here's the summary of these features. I used correlation plot at the beginning, as you would expect, because these are principal components. You're not expecting to see high correlation between the features and the data set. The other visualization method that I explored was kernel density estimates, which basically shows the distribution of each class for individual features. So in this case, the feature was the amount of transactions. As we can see, the average amount of transactions for fraud class is higher, and we see a relatively big difference between the mean and median of the features, which means that we have a lot of not outliers, but a lot of large numbers here, and the plot has actually been shown only for 2 standard deviations away from the mean. So we don't see really large numbers here just because they haven't been shown. And again, we can do this for every individual feature. And the reason that I did this was, this is a good way of getting a sense of what feature might be more useful in our analysis. So again, the features with low shared area between the two classes are more likely to help us getting good performance for the classifiers. And for example, features 22, 23, 24 are likely to be sort of useless in our analysis because you don't see much difference in distribution of the two classes. I scaled the data set because even though all the features were principal components, but the amount feature, as you saw here, was needed to be transformed into the right scale. And the other visualization method that I used was the TSNE, which stands for T-distributed stochastic neighbor, which is a nonlinear dimensionality reduction algorithm, which it's really helpful, especially when we are dealing with high dimensional feature variables. So this basically puts similar cases together and also handles nonlinearities very well. And similar to K-means, it clusters different classes. So in this case, fraud classes are the yellow circles and the regular transactions are the green circles. So yeah, so again, I train all the models that mentioned before. So regarding the criteria that I use here, so as I said, I use AUC, and specifically our focus is on AUC of precision recall, and mainly because all the classifiers do a good job of predicting the true negative class, but this problem, essentially, we are more interested in true positive class, which are, we would like to know which transactions are fraud. And the problem with using ROC then is that because the true positive class is always, basically TPR is always a large number, it becomes insensitive to the change of threshold, where this is not the case for this is not the case for precision recall curve, where the number of true positives and the number of false negatives are both sensitive to the threshold. So what would happen in all these cases is that we're always going to get good ROC, but precision recall curve would reflect a better measure of the performance of each classifier, and I've explained this more thoroughly throughout the report. So I think that was basically the main lesson that I learned, to, you know, what metric works better for which type of problem. And again, because in this case, we prefer to have more false positives, which mean the transactions that are actually regular, but the model predicts them to be fraud, than false negatives. So false negatives in this case would be the transactions that are actually fraud, but the model predicts regular. So you don't want that happen, because then in your credit report, there might be a fraud transaction, but the model predicts that one to be regular. So we want to have as many false negatives as we can. That's why we prefer high recall than high precision. Okay, so yeah, so we do this for, we train each model, and I forgot to mention here, because of high imbalance, I use a 9-to-1 ratio to split the data. Yeah, so we train each model, and then we plot the precision recall curve for each model. Some models work better than the other ones. I didn't tune any of the models to make the comparison between the performance of the models more fair. So yeah, so for decision trees and so on. So ultimately, k-nearest neighbors, random forests, and the gradient boost algorithms work better than the others. And because I didn't read the rubric before I started the project, I didn't know that we will have to create an ensemble and compare the performance of the ensemble with individual models. So in the first part of the project, I decided to find the best model and tune the hyperparameters for that model. So in this case, random forest shows really good performance. And so here I use the H2O library to tune the hyperparameters of the random forest model. And it's a really great interface. You can set the criteria to find the optimal parameters for each classifier. So in this case, I set the metric to be a UC of precision recall curve, and other parameters. There are a lot of parameters that you can set. Yeah, so then the next, yeah, so I managed to, the highest area under curve for precision recall that I obtained was 90.3%, which is really good. And actually all the other cross-validated cases showed really high accuracy, high AUC ROC, and high AUC PR. And the second part of the project, before that. So again, one of the good things about this library is that you can see the importance of each feature variable. And so in this plot, you see the importance of each feature. And so I decided to compare this with the KDE plots that I showed at the beginning. So here are what we get from for the best model in terms of the importance. And you can see that all the features that were more important, you can see that the shared area between the distribution of the two classes for each feature variable is relatively small compared to other features. So I think that was another thing that was important, that our first intuition was correct. So yeah, so the second part, then I created an ensemble of 3 models, so I had to start from the beginning because I wanted to use the same library. I limited the number of models to 3 models. So I trained a gradient boost, a random forest, an artificial neural network model. Where here I train these models, and then I create a stacked ensemble, and ultimately I compare the best base learner performance to the performance of the ensemble. And actually the ensemble did not outperform the best classifier, which was the random forest classifier. And keep in mind that the random forest classifiers are actually ensemble models where they sample, different, well, they create samples throughout the training set to make sure that they cover all the observations in their sampling and training process. Yeah, so I would say another lesson that I learned here was that in general, even though the ensembles improve the model performance, first of all, it's not always the case. In this example, random forest, as we saw in the first part as well, was outperforming other classification methods, which means that adding weighted average of the models to the ensemble will not necessarily mean that the ensemble is doing a better job in predicting the right class compared to the individual classifier, because the individual classifier is might be the best classifier among all the other classifiers. And the other thing to notice is that how much that bits of increase in the performance of the ensemble will actually help your industry. In other words, does it worth, adding and training many individual classifiers to create an ensemble to, let's say, increase the accuracy by 0.5%. So I think once we address these questions, then we can decide whether using an ensemble is a good idea or not. Thanks.